welcome. Today you'll be hearing about Nest's use of Cloud Platform to prototype massive scale services and using a philosophy I affectionately refer to as launching and iterating. So I'm Sam McVeety. I'm the tech lead of Cloud Dataflow, and I'm really thrilled to be joined today by Kevin and Peter from Nest. And most of the talk today is going to be their show because, we just built the infrastructure, they did all the hard work, so I'll give most of the time to them. But before then, by way of an introduction, I'll talk briefly about what launching and iterating looks like on Google's cloud, and then they'll go into a little bit more depth on what specifically Nest is doing and how they're building their services. So, launching and iterating. One of the things I really love about working at Google is this idea that you can take an idea and you can prototype it, you can see what works, what doesn't, tweak it, fail fast, succeed quickly if you're lucky, but you can do that and you can quickly make progress that way. And you're going to see how the Nest folks did that, and what I love about the cloud is it brings this capability to everyone. It's not something that is locked in at Google. It is something that anybody that uses Google Cloud has access to. So if you sort of take one thing away from this presentation, it's going to be, I hope it's this quote: one engineer, no systems background, and 3 days. And this isn't an outlier. This is how you can quickly use the cloud to validate ideas, to move forward, make progress, succeed quickly. For example, we had a hackathon recently on the Dataflow team, and this is what it looked like, where in a matter of days, people were building things on infrastructure and turning those ideas into a reality to say, hey, this is something we want to run with, or maybe not so good. So in making these things a reality, let's talk briefly about some of the tech that's available. So this first one is Google BigQuery. So this is your fast, economical data warehouse for large-scale analytics. And you can really throw all your data in here. You don't have to worry about indices or sharding. You just send all your data to BigQuery. You can use SQL, standard SQL, to ask questions about the data. And you don't have to know what those questions look like up front. You're not doing any sort of pre-optimization. So if it turns out that you're asking the wrong questions or you didn't know what questions you were going to ask, it's there to iterate on. And there's no backtracking, no repartitioning necessary. Now, to get the data there in the first place, you need something like App Engine. So this allows you to build a scalable web application quickly on any of the languages that Google's infrastructure supports. You can stand up a service simply, throw up some endpoints, and if we're talking about devices that you just want to send simple REST calls from, like for the Nest folks, this is a great way for them to phone home, send telemetry data quickly, and then you can analyze that offline. Now, if you want something a little more full-featured than SQL, that's where something like Cloud Dataflow comes in. So using the Apache Beam model, Cloud Dataflow provides a way to write your code and run it in batch or streaming mode. So up front, you don't know if you care about latency. You can iterate on your code while it's in batch mode, and then if latency turns out to be something you care about, you can run it in a stream processing fashion. Also, you don't have to worry about provisioning. It's a managed service, it has auto-scaling, so you're not worrying about replicas up front. You just say, hey, here's my code, I want to run it, I want to see how it works. And then sort of stepping back a level, in general, you don't even have to know which cloud you want to run on at first. If you want to prototype on Google's cloud, our commitment to open source means that if it turns out the investment isn't the right place, you can move because you're not locked in. So with BigQuery, for example, you have standard SQL support where you can run those queries elsewhere. For App Engine, you can take your container and run it on Kubernetes. And for Dataflow, you have this engine portability via Beam, where you can run that on the Dataflow runner, you can run that on Spark, anything that implements this standard. So altogether, this provides this ability to launch and iterate. You don't have to answer all these questions, provisioning all these things up front. You just have to have an idea, and you can validate that idea quickly without letting all these details get in the way. So thank you again for coming, and let me introduce Kevin from Nest.
Thanks, Sam. So I want to start here just by introducing Nest and a little bit about what our mission is and what we're trying to accomplish and how we're going to use the GCP infrastructure that Sam's team has worked on. So at Nest, our mission is to create a home that takes care of the people inside it and the world around it. And we accomplish this mission via the different products that we have. So we take unloved products in homes and try to reinvent them and make them smarter, make them do more for you. So we started with the learning thermostat, follow that up with a smoke and CO alarm, and then an indoor and an outdoor camera. But more than just the products, we have the app that's behind it that lets you actually interface with the device, your devices and your home, and the Nest service which sort of backs everything up. So Nest is sort of often considered a hardware company, but it's really much more than that, because the apps and the services that are behind everything are really the important bits. So, I'm part of the algorithms team at Nest, and I want to introduce a little bit what my team is responsible for. So we are the team that sort of takes the data from, takes our data and tries to make intelligent features for your devices. And so we have a principle at Nest that any data that's measured by our device should return value to you, the user of it. And we do this via features like Home Away Assist and Auto Schedule, which try to make sure that when you're not home or when you don't want your home to be heating or cooling itself, we can turn off your AC or your heating and make sure that you save energy. We also use our sensors to build thermal models of the home, and this lets us offer features like time to temp, so that when you change the temperature of your home, we tell you how long it's going to take to get there, so you know maybe you're leaving in an hour, you don't need to turn it to a temperature that it's not going to reach for 2 hours. Russia Rewards is a partnership with energy services and energy programs. This lets us actually pre-cool your home before maybe a time of day when it's going to be, energy is going to be very expensive, and this will let you save money, plus let the energy companies avoid these really high peak loads that can cause rolling blackouts. Steam Check and Sunblock are both features that fuse multiple sensors on the device to make the device smarter and do more. So with Steam Check, we can detect the difference between steam and smoke and actually build a smoke alarm that is less annoying, not going to go off at 7 in the morning when you get out of the shower, wake the kids up. And then with Sunblock, we can detect, is the temperature in the home actually going up, or is it just the sun has come through the window now and is hitting the thermostat, and we see a rise in temperature, but your home is still the same temperature, and we don't need to waste energy cooling it. So, my team's responsible for taking these features all the way from the very beginning, from maybe an idea, a sheet of paper in your lab notebook, through the production scale. And so what I want to talk about today is how we use GCP to really take these concepts from the notebook and show that they're feasible and worth investing in. So sort of at this very beginning stage, we're still trying to find out, is this possible? Is it something we can do? And so we don't want to invest a ton of the company's resources on an idea that we haven't even shown is doable yet. And so the first thing we need to do is build a prototype and collect data. And so at this scale, or at this stage, we sort of, sitting at a lab bench, maybe have a sensor that we've ordered from a manufacturer, or trying to figure out, can we measure the things we need to measure? And we found that each engineer had a very different method that they like to run their experiments, that they like to store and organize their data. Some people would use, a Google spreadsheet to keep track of all the experiments they were running. Other people would actually embed the different parameters in the file name itself so they could parse it out later. And this just didn't really scale. We weren't able to communicate very well, what each different engineer was doing, and it was hard to make that data available to the people that needed to see it to make their decisions early on. And so we were sort of faced with this problem of how do we collect and label data in a scalable way? And so we need to take data that's sitting on sensors, probably plugged into a laptop, maybe a Raspberry Pi, something like that, and get it to the engineers that are going to use it. And because this is GCP Next, you can probably guess how I'm going to go about this. So we want to build an app engine project to take that data, put it in a few data stores, and then feed it back to the engineers. And so we built a service and app engine that allows ingest and data querying. We use cloud storage, which is Google's object store, to store the blobs of sensor data. So this is temperature samples, humidity, smoke, things like that. that are really just CSVs or JSON blobs. And then the important bit here is using Cloud Data Store as a metadata service. And so here we can actually label our data in a sort of scalable way, a way that everybody can understand, and we can query that to get the data back. So we can say, give me all the experiments that were run at room temperature. Give me all the experiments that were run at 50 degrees C. So we can make sure that as we develop our products, we know exactly how they're working. And the first thing we found in building the service is that people wanted to use it. And so now we have the same data being used by the hardware engineers to validate their sensors. We have the same data being used by our embedded team as they're sort of trying to prototype and take these algorithms and put them on the devices. And what's more is this data was immediately available to them. So as soon as people collect the data in the lab, now they can immediately query it sitting at their desk running simulations, things like that. And then we can scale that up even further and plug this directly into our development infrastructure and our build system. So now, as we start implementing the algorithms on the device, we can pull that data down into the build system every time we have a new build and make sure the algorithm is still doing what we expect it to be doing. And this is really powerful for us because now we can do regression testing. We can make sure that as we develop new features, we don't go backwards on any of our other features. And finally, we can take that output from our build system and actually feed it back into the metadata. So now we have tags on all of our data showing which builds were successful, which builds weren't. We can start exporting this data into BigQuery and really doing analytics on it. So we can find out, is there a trend? Is there a pattern? Is there maybe a particular algorithm that has trouble at very high temperatures or very low temperatures? If there's a particular data set that had a bunch of events all happening at once, we can see that and say, maybe we have a timing problem on the prototype that we're working on that we need to dig into and make sure that our software is addressing that. And this sort of all can work because we have a common data set that's shared by everybody, and we know what we're trying to experiment on. And so this lets us build better algorithms because we have better data. And more importantly, we get to spend more time on collecting the data and less on all of the record keeping because the service handles the record keeping for us. And as Sam mentioned earlier, this whole service took one engineer that didn't have any services experience at all. The algorithms team is mathematicians, roboticists, machine learning experts. It doesn't cover any systems or services engineers. And it was able to be built over a 3-day period, which is really powerful. So now we're at the point where we've sort of proven the hardware. We understand that our sensors can collect the right information and we can sort of implement the algorithm. But algorithms don't exist in a vacuum. It's actually very important that we interact with the user during our algorithms. And so we want to understand how a user is going to use the different features on the device and how they're going to be affected by it. And so we need another service for this. To actually explore these different features. And so we have our Nest Cloud, which I've sort of shown here, that sort of interfaces between your phone or your laptop and all the different smart devices that you might have. But at this sort of phase of the product development, we're still very small. We're still sort of trying to figure out how this feature really works. And so what we actually want is a small service, something that we can iterate on really quickly. We can deploy maybe once every 10 minutes, deploy every hour, things like that. And we're just not ready to integrate it with our production app and our production service and go through all of the release processes that are needed there. And we want to make our algorithms engineers directly responsible for the logic and implementation so that if they find something that's not working, they can immediately address it and fix it. And so again, we can build a simple real-time service in GCP to do this. So we'll start with App Engine as our REST API that lets both the devices and the apps communicate together. We'll feed that through some algorithm logic to implement whatever feature we're looking to implement, and then store the state of the device in Cloud Data Store. This lets us use Cloud Data Store as sort of the backing store that either an app or a device can query to figure out what's going on. So you might imagine storing temperature data there or something like that. And again, we can export this to BigQuery to let us do analytics on how a user is interacting with the device. So we can store a record of, did the temperature get changed by the app or by the device, and which direction is things flowing? Do people prefer to use the device to change the temperature, or do they prefer to use the app to change the temperature? And we're fortunate at Nest to have a very active internal test group, so we can actually get quite a good set of data from just all of our internal employees trying things out for us. So I want to walk through just a little bit of how simple this actually is to build by showing a bit of code here. So the first thing we wanted was real-time state communication. So we want the apps and the devices to communicate together. And this we'll do with App Engine, and specifically in Python here with using the Web App 2 web framework. And so we just need two functions here, a get function and a post function, so that we can update the state and we can fetch it back. And then we use Cloud Data Store to actually store the data, sort of do all the heavy lifting for us. And the APIs that Google Cloud provides are really simple here. You can see in the get function, we just create a key using the device ID and fetch the data and write it back out to whoever called that function. And then for sort of similarly in reverse, we write the data directly into Cloud Data Store. Cloud Data Store is NoSQL, so we can add or remove fields as we need. And it's very easy to update this. And it really is just these 10 lines of code that let us do this. And so the next step we want is using BigQuery for analytics. So this lets us sort of track how things change over time. And the BigQuery streaming API lets us really quickly send data over to BigQuery and make it immediately available. So now we can very quickly sort of look at things in real time and don't have to wait to do our analytics, the day after. We can iterate much faster, as Sam was talking about. And again, because all of this is sort of an integrated part of GCP, it's very quick. Getting credentials for authentication is just a couple of lines at the top. That means that we don't have to worry about implementing our own authentication mechanism, anything like that. And we can be guaranteed that it's a secure system. We can know that only this App Engine application is allowed to talk to this BigQuery table to send data over to it, and not worry about configuring it ourselves. And then again, at the bottom, it's just a very simple API call using the libraries BigQuery provides to send data over to that service. And then finally, we can use this service to explore higher level logic. So instead of just persisting and logging state, we can actually implement this complex logic. And so here I've sort of put a function in the middle that I've labeled apply logic, which sort of sounds like cheating, but it really isn't, because all it is a Python function. And that's the magic, is that we don't have to do a whole lot of extra work. We just write a Python function that takes some existing state and new state and does some arithmetic or does some logic and figures out what we want to do. And this lets us iterate, again, very, very quickly, so that if we want to try something out, we don't have to go through the process of creating a build for the device, validating that that build's not going to brick the device, and then doing a rolling software update on our test devices. We can actually just very quickly change something in the service, redeploy, see how it's going, and keep doing that over and over until we have something that works well. There are a bunch of other useful things that are just sort of hidden away in App Engine that make developing pretty easy, or pretty remarkable. And one of these is the deferred library that I've highlighted here. So this lets you schedule things to happen later by taking advantage of the App Engine task queue. And so here I'm deferring the BigQuery insert, because that can sometimes be an operation that maybe takes a little bit of time, and so we don't want to put that in the real-time loop of devices fetching state. And so we just do that sort of asynchronously. And then additionally, I've written this to schedule a callback. So in 300 seconds, that callback function will execute, and maybe we can make a different decision than we made up front, or reconsider the decision we made initially. And that, again, is a very powerful thing to be able to do, and it's even more powerful that we can do it with a single line of code. And all of this sort of has the function of making services easy for us. So everything just sort of scales. Data Store, BigQuery, App Engine are all things that just scale by default. And so we don't have to worry when our little 10 devices that we were testing on all of a sudden becomes the whole company trying out our product. You never want to be in that situation where you have to tell someone, oh, I just built this on my desktop and I can't let anybody else use it. Now we can make sure that everything that we're building, anybody in the company that needs to use it can use it. We don't have to spend any time managing VMs. Again, not a services engineer, not a systems engineer. I don't want to make sure that I've closed all the right ports on some machine somewhere. Because App Engine's the interface, it's sort of secure by default. And the built-in OAuth authentication lets us use all of the Google services and make sure that those services are secure, and that the only data that the data can only be accessed by us. And really, we get to focus on the logic and the applications, which are the bits we're good at, and let Google focus on the mechanics, which is the bits they're very good at. And then from there, I'm going to turn it over to Peter, who's going to tell you about how we scale all this out and monitor it in production.
So, hi, my name is Peter Grabowski. I'm the tech lead and manager of the data integration team at Nest. I wanted to start off by saying thank you to Sam for giving us a great overview of the managed technologies available within Google. And a thank you to Kevin for a great walkthrough of how his team develops and prototypes algorithms at Nest. So, I'd like to talk to you today a little bit about how we think about scaling out those algorithms, the systems that make them scale, and also once they have been deployed, how we monitor them and make sure they do what we think that they're doing. So this is our architecture. To get started, I'd like to give a quick tour through our architecture. This won't be the focal point of the talk, but it will come in handy and provide some useful context for later in our discussion. One of the things I wanted to highlight right away is that, as Sam mentioned, we've got both open source and managed technologies here, and being able to co-locate those gracefully within the same environment was a major draw for using GCP. So you can see some managed technologies that Sam talked about. You've got Dataflow and BigQuery. You can also see some open source technologies that we use, like Apache Storm, Apache Kafka, and Hadoop HDFS. So our system begins, like many others, with a data logging service. We've got many devices out in the field. We've got cameras, we've got smoke detectors, we've got thermostats. They're all sending data up to the service. They're sending it up in different formats. They're sending it up in different sizes. They're sending it up in different shapes. No matter what size or shape they're sending it up in, it's received by the data logging service. This sits out in front of our architecture, and it's responsible for three things. So it's designed to be very purposely straightforward. It receives the data, it authenticates that the data came from a Nest device, that it's not someone trying to spoof us, and then it writes it to a durable store. From there, we move to the processing layer. The processing layer is made up of Storm and Kafka. On the Storm side of things, we've got one topology that is responsible for each kind of data that we process at Nest. But no matter which topology it is, no matter which data source it is, the topologies do the same thing. They extract the data from whatever format it's in, they transform it into Avro, and then they load that data into Kafka. From there, we move to the loading layer. The loading layer consists of Cloud Dataflow, and I want to highlight one of the really nice features of Cloud Dataflow, which is, as Sam mentioned, it can run in both batch and streaming mode. So this might sound like a simple thing, but it ends up making our operational workflows a lot easier. We can use streaming mode for streaming data in real time for the normal operation of the service, but we can also use batch mode by just changing a few lines of configuration to do historical backloads or particularly large load jobs. So this simple feature ends up saving us a ton of time. From there, Dataflow writes into our storage layer. We primarily use BigQuery, although as I mentioned before, we also maintain a footprint in Bigtable and HDFS. And so up until this point, what we've seen so far constitutes our data platform. Everything else that we're going to talk about now constitutes the applications, or applications that run on top of the platform. We've got a number of different applications. We've got some monitoring applications and reporting applications that help us make sure our devices are doing what we think they should be doing, and also that our general fleet health is strong. We've got machine learning algorithms that come from Kevin and his team that we've scaled up to run on production. We've also got a number of analytics applications or various workflows from our consumer analytics teams. And finally, a number of consumer insights that we take and transform the data from the devices back into value for our customers. I'll talk about two of my favorite consumer insights applications later on in the presentation. So at this point, we're at a point that I'm sure many of you have been at before. We've got all the data loaded, we've got all the data stored. Now what do we do with it? So we had the same question. We went out and talked to all of our device teams, the camera team, the smoke detector team, the thermostat team, all of the algorithms teams to see what they might like to do with it, all of the analytics teams to see how they might like to use it. And no matter the team that we talked to, the results came back the same. They wanted to be able to do fleet-level analysis quickly and easily. So to help them out, we built our first prototype. We built it using PySpark and Zeppelin, two great open source technologies out of Apache. It looks something like this. And I'd like to take a minute to walk through it. So this was HVAC Runtime is calculated with PySpark. For those of you who aren't familiar, HVAC stands for heating, ventilation, and air conditioning. So it's a measure of how much time your furnace or how much time your air conditioner was running throughout the course of a day. You can see on the x-axis here, we've got fraction of day with HVAC running. This is a histogram. On the y-axis, you've got the fraction of the device population. So all the way on the right, you see that about 5% of the population was running 100% of the day. All the way on the left, you see about 20% of the population was running not at all during the course of the day. This might be alarming, except for that this data came from a set of test devices. So that leads into one of the major complexities that we found with this system. It was really costly to run analyses like this on all of production. We had the capacity to run it on production, and for the most important workflows we did, but if you wanted to think about other types of workflows, it became really tricky to do so. One of the main reasons this was so tricky is that our storage was coupled to our compute. So unless we picked exactly the right instance type with exactly the right amount of RAM, exactly the right amount of storage, and exactly the right number of CPUs, we always had too much of one and not enough of the other. I was describing this problem to my roommate as I was preparing this talk, and she mentioned that she had the same problem, except for she had it when she went to the store and she bought chips and she bought salsa. So no matter what, she always had too much of one and not enough of the other. We've got the same problem at Nest, except for we've got it with storage and compute. Of course, that leads to frequent resource contention. We had one cluster where the data were located. We ran both high priority workflows on it, but also lower priority analytics tasks, which meant that the lower priority analytics tasks were frequently preempted or bumped from the workflow. This meant that our analytics team had to either go back and reschedule or rerun those workflows or have gaps in their analysis. That also meant that our team took on the role of a part-time sysadmin. We got, excuse me, we got many phone calls saying, hey, this workflow's just been killed. It's run out of memory. Can you help us get it running again? Which wasn't a great working environment for the team. There were a number of operational complexities that we ran into as well. So PySpark and Zeppelin were great tools, but they weren't built to do this sort of dashboarding. So we ended up building a separate service that was responsible for generating JSON blobs that represented these templates that we wanted to create, loading them into the notebook cache of the Zeppelin monitor, restarting the service so the Zeppelin monitor picked up on the new notebooks. This worked well for one user, but you can imagine as multiple users started trying to use the system and it was frequently restarting all the time, it wasn't a great experience for them. Additionally, there was a constraint that there was a maximum number of notebooks that could be loaded on the machine at once. So we had to build a second service that was responsible for backing these notebooks up to durable store and then pulling them back in when we needed them. It wasn't a great experience for the people who wanted to see the data. This next point is an especially important one. I want to take a moment to talk about it. One of the things that we care most about at Nest is protecting our users' data and protecting our users' privacy. And many of the mechanisms that from the systems that we were using provided only clunky authentication and authorization, which made it difficult to do the fast and flexible data analysis to return value to our customers. Similar problem was that it became very difficult to build analyses back to different teams. So, for example, imagine that the thermostat team came to us and said, hey, we've got this great new data type that we want to store. We know that your cluster is full. We know that we're going to have to expand the cluster. What's it going to take to load that data type in? It was difficult to figure out exactly how much that extra space would cost. We had some heuristics to help us come up with estimates. They always proved to either be too high or too low. And so in the end, we ended up building most of the cost back to our team, which was great from a billing perspective or a management perspective, but terrible from a team bottom line perspective. And finally, if you were an analytics team that had already generated some data that you wanted to use to augment or color your analysis, it was difficult to get data into the system. You had to learn a new set of tools, you had to get the appropriate permissions, and then you had to figure out how to join and link those two together. So I'd like to take a little bit of time to talk about the solution that we came up with. So on the left here, this is a zoomed-in view of the architecture that we discussed previously, and it starts with the events in Cloud BigQuery up at the top. So those events are the same events that were loaded from Kafka into BigQuery by Dataflow. Once we've got the data available in BigQuery, we then built a processing library on top of it. The processing library was responsible for two different pieces. One, there's a number of Nest-specific nuances in our data set. So the processing library was aware of those nuances and provided a higher level abstraction on top of them to make it easier to work with. And two, one of the most frequent kinds of analyses that we do at Nest is time series analysis. So it provided a number of very useful higher level abstractions for time series analysis. One of the really nice things, as Sam mentioned, was that even though we're running in Cloud Dataflow, the code is just Apache Beam. It's completely open source, completely portable. So if we wanted to, we could pull this code out of Dataflow and run it elsewhere, run it on our own cluster, run it wherever we might want to. We're not planning on doing that. We love working with Dataflow, but it is really nice to have the flexibility to do that. Wherever we do the computation after it's complete, we load the data back into BigQuery for further processing or analysis. And from there, there's a number of really nice integrations that make it easy to visualize. Two of my favorites are up on the screen. You've got Data Studio and Data Lab, but it's also got really easy connectors for Excel or Tableau or Google Sheets or whatever you might want to use to take a look at it. So I'd like to talk about a couple of advantages from using this system. First and foremost was auto-scaling. This auto-scaling was huge for us. It made it really easy for us to develop code locally, to test code locally, and then to push it out to our production cluster to run at scale by only changing a few configs. And to demonstrate how powerful this was, I'd like to tell a short story. We had a camera systems engineer who was a great engineer, but again, didn't have too much familiarity with building services or analytics workflows. He was able to get up and running using the libraries we created in only a day. So there was a huge operational advantage from using this system. Part of the reason it was such a big win was that we were finally able to decouple storage from compute. So as I mentioned before, all of the storage was handled by BigQuery. All of the compute was handled by Dataflow. So we could add new logs to this system without worrying about scaling out Dataflow, or we could add new analysis pipelines without worried about scaling out BigQuery. And finally, because everything runs as a managed service, there was no more resource contention with production jobs, which meant that the analytics teams could run their jobs without worrying about backfill, without worrying about backfill, and also without worrying about having windows or missing windows in their data sets, and that our team got many fewer late-night phone calls. There are a number of operational advantages as well. This first one is a big one. They've got this really nicely defined access control model that made it really easy for us to grant people access to the right data at the right time and only when they need it. So their access control model was great and increased our operating security. Similar system, we're finally able to bill analyses by team. So whenever you kick off a workflow, you're able to set a billing config or billing ID. That means that the teams that kick off workflows are billed for only the compute cycles they use and nothing more. And finally, as we mentioned previously, really great options for data visualization. Data Studio, Data Lab, Tableau, anything that you want to work with is available. So I'd like to revisit one of the example use cases that we talked about before. This is the same HVAC runtime analysis, except for this time it's computed with Cloud Dataflow. So on the x-axis, you see the day that it ran. On the y-axis, you see the fraction of time that your furnace or air conditioner was on. It starts out low in October while things are still pretty warm. It increases through January 10th, where there was a huge storm in the Northeast, and then it falls back off as things start to warm up in the spring. This is a really simple computation, but this graph hides a really important fact. This is one of the first times that we were able to run an analysis like this on all of production. So all of those sampling pieces that I talked before, where you're worried about getting the wrong population or missing population or masking populations, we don't have to worry about. This is great if you want to build more complicated or more nuanced machine learning models on top of the data. You can be sure that you're hitting all of the points. So with that, I want to highlight that even a simple computation like the one that I just mentioned, even just figuring out HVAC on and off periods, can have some really positive returns and value for our customers. This is one of my favorite products that we offer at Nest. This is the monthly energy report. So every month, we email our Nest users and say how much energy you used, as compared to last month. We try to sprinkle a little machine learning on top of it to say why your energy usage changed. Maybe it got colder. Maybe the weather changed. Maybe you adjusted your thermostat to be more comfortable in your home. We also provide one of my favorite statistics at Nest. So every month, we give a summary of how much energy people have saved by installing Nests across the entire population. This is the one from January, so this is current through January 31st. Since October 2011, Nesters have saved 11.3 billion kilowatt hours, which is enough energy to freeze all of the ice necessary for 2 million ice skating rinks. So that's a pretty cool insight that comes out of a relatively straightforward data analysis once you're able to perform it on the entire fleet. It's also a lot of energy to save simply by installing a thermostat. Fast and flexible data analysis also lets us help prove how efficient our devices are. So we're really proud to announce that Nest was the first thermostat in America with an ENERGY STAR certification. And some of the fast and flexible data analysis techniques that I talked about helped us be able to prove this efficiency out. So with that, I'd like to wrap up. Using the technologies available to us within GCP provided an easy path from development to production, paved by shared and scalable tooling throughout. So that means that an algorithms engineer like Kevin can develop and prototype data sets using one set of tools, and then take those same tools to do analysis when he deploys the algorithm to production. There's no need to learn another tool set for doing data at scale or for doing smaller data analysis locally. The access control models they provide give the right people the right access to the right data at the right time. And similarly, the billing operations that they allow for allows you to build the right teams for what they use, and more importantly, for only what they use. But most importantly, the data availability and access controls provided by GCP help us further our mission of creating the home that cares. So with that, I'd like to thank you to all of the team members at Nest and Google who contributed to these projects. These weren't built by a single person. We have a great engineering team at Nest, some of them who are here today that are wonderful to work with. We've got a great engineering team at Google, including people like Sam, who have helped us along the process. So thank you to both. And I'd also like to thank you in the audience for staying and listening. We'll be outside after the talk. Feel free to come up, ask any questions that we might have, say hello. And like I mentioned, we've also got some other data services engineers from Nest who can help to field questions or provide more information. So thank you.